Welcome back to the deep dive. We are shifting gears today. Usually we're talking about history or, psychology, some big global shift. But today, we're tackling something that I think scares a lot of people, computer programming. But before you panic and reach for that stop button, I promise we are not just going to be reading lines of code today. We're looking at a concept that actually explains how human beings solve big problems. It's called modularization.
It sounds like a mouthful, doesn't it? Modularization. Sounds very technical. But you're right.
But
While it is the absolute foundation of how software is built, it's also really a philosophy of organization. It's how we keep complexity from just, well, crushing us.
Exactly. So we're working off a presentation, Chapter 9, Introduction to Programming, and it zooms in on functions and methods. Basically, our mission is to figure out how programmers take the absolute chaos of a complex app. I mean, think about everything your phone does and organize it so it doesn't just crash every 5 seconds.
And the secret is breaking things down. That's really the core theme today.
Right. And we're going to talk about why writing good code is apparently a lot like designing a house. And we're going to get into this idea of the black box, which sounds mysterious, but it's something we use every single day. So let's set the stage. I look at modern software, right?
Yeah.
Video games, banking apps. The complexity is insane. Millions of lines of code. How does a programmer keep all that straight in their head?
Well, the short answer is they don't. No one keeps the whole program in their head at once. It's cognitively impossible. If you tried to write a modern app as just one giant list of instructions, step 1, step 2, all the way to step 10 million, it would be a disaster. You couldn't read it. You couldn't debug it. So we use modularization. We break the program into smaller, manageable, independent units. And in the material we're looking at, these units are called methods or functions.
Okay, so a method is like a mini program inside the big program.
That's a great way to think about it. Yeah. It's a reusable piece of code designed to do one specific task. Instead of building the whole car at once, you focus on building the fuel injector, then the brake pad. Then you put them together.
The source material uses this analogy that I absolutely love because, well, I'm addicted to caffeine. They compare a method to a coffee machine.
It's a classic analogy for a reason. It perfectly explains what we call implementation hiding, the black box idea. I mean, think about your morning. You walk up to the coffee machine, you know what it does. Now let me ask you, do you know exactly how the heating element works inside that thing?
Absolutely not. And honestly, at 6 in the morning, I don't want to know. I just want the coffee. I press the button, and it happens.
Exactly. You treat the machine as a black box. You don't see the internal details. That's the method body in programming. All you see is the interface. You press a button, that's calling the method.
So the machine is the method. Me pressing the button is the code calling that method. And I assume the choices I make, large or medium, espresso, those are important here too.
They're crucial. In programming, those are your parameters, your inputs. You're feeding specific information into the black box so it knows what to do this time. You give it inputs, large, espresso, and then the machine gives you a cup of coffee. That's your return value.
The output.
The output. So you have the call, the parameters, the hidden body, and the return value.
This makes so much sense. Because if I had to manually wire the heating element every time I wanted coffee,
Yeah, I'd never do it.
I just drink water.
Yeah.
It wouldn't be worth the effort.
And that's reusability. Once that make coffee method is written, you can use it 1,000 times. Plus, you get separation of concerns. The coffee machine makes coffee. It doesn't toast your bread.
Right. And if the coffee tastes bad, I know it's the coffee machine's fault. I don't go check in the toaster.
Precisely. Ease of debugging. If your calculate tax feature is wrong, you go to the calculate tax method. You don't have to search through all the other code.
Okay, so we got the concept. Let's look at the anatomy. The source breaks a function down into 3 parts: header, body, and return statement.
Right. The header is like the label on the box. It tells you the name, who can use it, and what kind of thing it gives back.
And the body is the secret sauce inside.
Yep. That's the logic, the actual work. And the return statement is what hands the result back to whoever asked for it.
Okay, now I notice there's a distinction about return types. Sometimes a method gives you a number, but sometimes it says void, which sounds a bit existential.
It does sound a bit dark, doesn't it? But it's actually really common. Think about that coffee machine. It returns a physical object, the coffee. In code, that might be a method like int add numbers, which returns the sum. It calculates 2 plus 2 and hands you back a 4.
Okay, so I get something back I can hold on to and use.
Right. But imagine a method called print greeting. Its job is just to display hello on the screen.
Like
It
just
doesn't calculate anything for you to use later. It just
okay.
performs an action and finishes. That's a void method. It returns nothing.
Got it. So getTemp might return 98.6, but print greeting is just a task that happens.
Exactly. And the source also mentions returning a simple true or false, which we call a Boolean, like a method is even. You give it a 4, it returns true. You give it a 5, it returns false.
Simple enough. Now, there was another concept in here about scope. Local versus global variables.
This is crucial for keeping your sanity as a programmer. Imagine you have a variable named x. If every part of your program could change x whenever it wanted.
Total chaos. You'd have no idea who changed what.
Right. So we use local scope. A variable created inside a method is invisible to the rest of the program. What happens in the method stays in the method. It's private.
Like a Las Vegas rule for code.
Exactly. Whereas a global variable is accessible by everything. They're useful for shared data, like a high score, but you have to be very, very careful with them.
It's not going to stay safe.
Oh.
Okay, let's go back to those inputs, the parameters. The source makes a big deal about how they make code dynamic.
Well, think about a method called greetUser. If you write it to specifically say, hello, Alice, that's not very useful when Bob logs in.
Right. I'd have to write a whole new message for Bob. And one for Charlie.
You'd never finish. But if you use a parameter, let's call it name, you just write greetUserName. Now you can pass in Alice, and it says, hello, Alice. Pass in Bob, it says, hello, Bob. The code adapts.
That's way more flexible. And you can have multiple parameters too, right? Like taking a name and an age.
Yes, print details, string name, in age. You can mix and match.
Now, here's where it gets really interesting to me. Method overloading. This sounds like we're working the method too hard.
No, it's actually a convenience. Overloading means you use the same name for a method, but you just give it different parameters. The computer figures it out.
The alarm clock example from the slides was perfect. I do this on my phone all the time.
It's a great real-world example. You might have a method called setAlarm, version 1. SetAlarm int hour. You just give it a 7, and it sets an alarm for 7:0. Version 2, SetAlarm int hour, int minute. You give it 7 and 30. Now it's 7:31. And version 3. Set alarm, int hour, int minute, string label, you give it 7:30 and wake up.
So 3 methods, all named setAlarm, but the signature, the combination of inputs is different.
Correct. The signature acts like a fingerprint. The computer looks at what you gave it and matches it to the right version. It's just much cleaner.
That is much cleaner. Okay, I need you to walk me through this next part because I feel like this is where students get tripped up. Pass by value versus pass by reference.
Yes, the classic stumbling block. It's all about what actually gets sent to the method. Do you send the original or do you send a photocopy?
The source compares it to a copy versus an address.
Right. Let's start with pass by value. This is for simple things like numbers. Imagine you have a piece of paper with the number 10 on it. With pass by value, you photocopy that paper and give the copy to the method.
Okay, so the method has a sheet that says 10, and I have my original sheet that says 10.
Exactly. Now, if the method scribbles on its copy and changes the 10 to a 20, does your original paper change?
No, mine still says 10.
Exactly. The original is untouched. That's pass by value. It's safe. The method can't mess up your original data.
Okay, that feels safe. But then there's pass by reference.
Pass by reference is for bigger things, like arrays. Imagine you have a huge filing cabinet. You can't photocopy the whole cabinet every time. It would take too long.
So what do?
You give the method the address. You say, the data is at 123 Main Street. This is pass by reference.
So I'm giving the method access to the actual original data.
You are. And here's the danger. If the method goes to that address and rearranges the furniture, if it changes a number in that array, the change is permanent. It affects the original.
That sounds risky. Why would we even do that?
Efficiency, speed. If you have an array with a million numbers, copying it is incredibly slow. Passing one tiny address is instant. So we accept the risk for the performance boost.
Power comes with responsibility.
Yeah.
You have to trust the method not to trash your house.
As always in programming, it's a trade-off.
Moving on to design. The source uses a house analogy to explain cohesion and coupling. The comparison really made it click.
It's all about organization. The source describes a bad design as a house where the kitchen, bedroom, and bathroom are all in one single room.
Which sounds like a terrible studio apartment in New York City.
It's a nightmare. In programming terms, this is low cohesion. The method doesn't have a single clear purpose. It's trying to do everything at once.
And the source says this leads to tight coupling.
Right. In that studio apartment, if the plumbing breaks, you can't cook because the floor's flooded. Everything is tangled together.
So good design is just having distinct rooms.
Exactly. High cohesion means the kitchen is only for cooking. A method cook meal should just cook the meal, not also try to clean the floor.
And that leads to loose coupling.
Yes. The kitchen doesn't depend on the bedroom. If you remodel the bedroom, the kitchen keeps working. It makes code so much easier to maintain.
It's funny how these computer science principles are really just life principles. Focus on one thing. Don't let your problems tangle up.
Modularization is absolutely a life philosophy. You have to break things down.
Okay, we have to talk about the mirror effect, recursion. The source defines it as a function that calls itself. This feels like the movie Inception. How does this not just create an infinite loop?
It will crash the computer if you're not careful. That's why the source emphasizes the two rules. You need a recursive case, where it calls itself, but more importantly, you need a base case.
The stop sign.
The stop sign, the condition that says, okay, we're done, stop calling yourself.
They use the Fibonacci sequence as the example.
The classic example. The sequence goes 0, 1, 1, 2, 3, 5, 8. Each number is the sum of the two before it.
Right.
So a function Fibonaccian just says, to find the answer, go calculate Fibonaccian-1 and Fibonaccian-2 and add them.
So it calls itself asking for smaller and smaller numbers.
Yes, it keeps drilling down, creating this tree of calls until it hits the base case when n is 0 or 1. Then the answers bubble all the way back up to the top.
It sounds elegant, but the source mentions a trade-off.
It is elegant, but it can be heavy on memory. Every time it calls itself, the computer has to remember where it was. We call that stack overhead.
And if you forget that base case,
If you forget the stop sign, it calls itself forever. The memory stack fills up, and you get a stack overflow. The program crashes.
so use with caution.
Use with caution. Often, a simple loop is more efficient, even if it looks less cool.
Before we wrap up, the source touches on planning, because just sitting down and typing code is a bad idea.
Terrible idea. You need a plan. The source suggests IPO charts, input, process, output.
Simple enough. Input, length and width. Process, multiply, output, area.
Exactly. If you can't write it on a napkin, you can't code it. It clarifies your thinking before you get lost in semicolons.
And speaking of not getting lost, the source also mentions predefined methods. Basically, don't reinvent the wheel.
Please don't. Every major language comes with a massive library of tools that are already written, tested, and optimized.
Like math.sqrt for square roots or arrays.sort.
Right. Could you write your own sorting algorithm? Sure. Will it be as fast and bug-free as the one built into the language? Probably not. Use the tool.
So let's bring this all home. We've started with a coffee machine, understanding a method is a black box. We moved to the house layout, understanding that good code keeps tasks separate. And we looked in the mirror of recursion.
It's a journey from the brick, the method, to the architecture of the whole building.
And for the listener, why does this matter if they aren't planning to be a software architect?
Because modularization is how anything big gets built. Whether you're writing a novel or planning a marketing campaign, you can't do it all at once. You have to break it down into modular tasks. It's a way of thinking that conquers complexity.
That's a great takeaway. And I want to leave everyone with a thought that struck me about implementation hiding. The black box. We rely on it. We drive cars without knowing how fuel injection works. We use phones without understanding silicon chips.
We trust the interface.
We do. But in an age of AI where the black box is getting smarter and more complex, are we becoming too comfortable not knowing what's happening inside? It's great for coffee, but maybe we should peek inside the box more often when it comes to the algorithms running our lives.
That is a very valid question. Convenience always comes at the cost of understanding. Sometimes it pays to open the hood.
Something to mull over. For those of you who are students listening, check Canvas for your assignments. Nothing due right now, but come to class ready to learn.
See you there.
Thanks for listening to The Deep Dive. Catch you next time.